This conference will now be recorded.
Yeah, thank you. I just wanted to say as well that if you raise any questions in terms of understanding the content or anything I'm explaining, Paul, could you just kind of interject and I'll explain it at the time. I guess all the other subject matter questions we'll pick up at the end.
Yes.
If that's okay.
I'll do that, Matt.
Sure. So yeah, I'll be talking about HS2 railway systems, focusing on high-speed track design. There's three kind of broad sections to the presentation today. I'll give you an overview of HS2 and where we currently are today. Then I'll give an overview of railway systems, or what we're defining as railway systems, and then focusing on high-speed track design and some hot topics associated with that. And then at the end, I'll spend a little bit of time just explaining our approach to systems integration. The intent behind that is how we bring all of these railway systems together into a functioning railway. So just a bit of background to the project, if you're not familiar with it so far. So the entire route will be 345 miles of new track spanning between London, Manchester and Leeds. And then there's connections into the existing network as well, which I'll go on to explain now. So we have phase one running between London and Birmingham with a connection into the existing network around Handsacre, just here. And then we have the second phase of the route, phase 2A, running between Birmingham and Crewe. And there's a connection into the existing network at Crewe. Phase 2B of the route runs from Crewe to Manchester, and on the eastern leg, Birmingham to Leeds. And we have a connection to the existing network around Goulburn towards Wigan, just west of Manchester. On the eastern leg, a connection just south of Chesterfield, and a connection to the East Coast Main Line just beyond Leeds, next to York. So originally it was a two-phase build programme, but the section between Birmingham and Crewe was accelerated because of the engineering and the stakeholder engagement was seen as more straightforward than the other sections around Manchester, the East Midlands and Leeds. Hence why the second phase is now split into two, with phase 2A and phase 2B. So why are we building HS2? So the fundamental purpose is around capacity. So if we take the longer commuter journeys or the intercity journeys in the UK between major cities and move them onto dedicated infrastructure, we're then creating more capacity on the existing network for local commuter services and increased freight paths. I think we can all recognise that in terms of environmental impact, the railway is the most efficient means of mass haul, so both for moving passengers and for freight. So improving the whole network of the UK is absolutely fundamental for us achieving the obligations the government setting around being carbon neutral by 2050. And obviously better connectivity, linking cities, linking stations is good for business, it's good for people visiting friends and family, and bringing cities closer together. So in terms of where we are now, the most significant works that have started are associated with our main work civils contracts. So the earthworks, the tunnels, the viaducts between London and Birmingham, so phase one. There's 4 organisations involved in that route section, with the works amounting to about £12 billion worth of work. So in the northern part of the route between Birmingham and the Birmingham interchange and just south of there, Balfour Beatty Vaughan are responsible for delivering that section of civils work. Then just south in the northern central section, we have EKFB, so a Farge, Kia, Ferrovial BAM joint venture. And then we have a line working on the Chiltern Tunnel and Colne Valley Viaducts, 2 of our most challenging engineering structures. They are responsible for delivering. And in terms of recent progress, you may have seen last week the first TBM has started boring last Thursday, and that was for the Chiltern Tunnel in the Align section. And then the section further south, so out of London Euston towards the Chilterns, SCS joint venture are responsible for that. So they have some very complicated interfaces around Euston, which we can discuss a bit more. So in terms of stations as well, we have separate station design contracts. I wanted to include some visualizations here so you could see what the stations would look like. We also have London Euston Station, which is the most complex in terms of stakeholder interfaces and complexity of working alongside the existing station. Both Birmingham Curzon Street and London Euston present a fairly unique challenge for track system design, because we're also intending at these locations to discharge toilet waste from rolling stock, because the rolling stock on HS2 will be the first operational fleet in the UK to include bioreactor toilet technology, where we're actually treating the waste on board. And in terms of then cycling the rolling stock between the depot and its use in the timetable, we need a means of emptying what's referred to as the grey water, so removing some of the fluids whilst the trains are still on the network. But that won't be every time they visit the station, it will be at strategic timings. But we, in terms of making the planning work with the rolling stock fleet size, we need to design for that within the station. And that's created particular challenges around integrating the drainage, and we foresee a need for a cast in situ approach for within the station integrating treated drainage channels to accommodate that. So just an interesting challenge that arises from the station design. In terms of the operational challenge, HS2 itself is inspired by the Tokaido Shinkansen in Japan. They have a very similar kind of need in terms of the network structure to the UK, in terms of it's a relatively long and thin country, so they need a core network of high capacity. We're quite different to France and Spain, and even China, which have a more grid-like or radial structure to their networks. So either they run in a grid pattern or lines run out from a central core, whereas we have lots of locations we want to join up in the UK, but through a central spine of the network. So that's why there's good alignment here with Japan's approach to building their infrastructure. So we know we need a high capacity, as I've mentioned. So the way to think of it is we're a bit like a metro service or the London Underground service, running many trains per hour, but at a high speed, and that creates its own challenges, which I'll come on to. An interesting takeaway as well is that in Japan, they have no functionality for bidirectional running on the high-speed sections. And with HS2, we're foreseeing that there's no realistic opportunity of having a degraded mode of operation. So there'll be broadly three phases: either we're running the service, or we're not running the service, or we're in a catch-up mode to return the service. There's very little opportunity to run a reduced service. So everything that goes into our engineering and our planning is based on running that very highly reliable service and taking care of faults outside of the operational period. So in terms of the challenge in delivering this, I've included here, these are kind of disciplines and areas of engineering input within HS2 as an organisation, and these aren't all of them, but some of the key ones we certainly get involved with track and the subsystems of track as well. And I just wanted to highlight here the complexity of the stakeholders, the engineering input, and everybody having to work together to achieve an end state operational railway. If we all work in silos, that's not going to happen. So we need an approach which integrates all of these people together. So in terms of railway systems, it's not all about speed. So you'll be forgiven for thinking it is, given we're called High Speed 2, but I've alluded to the fact around capacity and reliability. I actually think the biggest challenge we've had to date so far with the track system, apologies, The biggest challenge we've had to date with the track system design is around reliability of the system. So particularly around switches and crossings as well, we've put a lot of effort into understanding the functionality of that system and how we can ensure reliability. In the rail systems context, it's not too much of a ridiculous statement to say we're effectively designing two railways in the footprint of one. There's a lot of diverse routing when it comes to power or the command systems or the condition monitoring systems. We're effectively building two sets of systems so that if the first one fails, we don't have a shutdown of the railway. And then in terms of capacity, particularly for the signalling system, that creates some real constraints in terms of squeezing as many trains as we can into the track section we have available. So there's quite a bit to be considering here. We don't just engineer it for the high speed, we're pushing the boundaries when it comes to reliability and capacity as well. So in terms of railway systems within HS2, the purple boxes on the screen here explain what we define as our railway systems. So starting in the top right, obviously we are an electrified railway, so we have a connection into the national grid that forms our high voltage power supply, which powers the overhead line equipment. We then have a contract dedicated to tunnel systems, or the systems within the tunnel in terms of water supply, local power supply, the cross passage doors for and the ventilation for emergency situations and maintenance tasks within the tunnel. We have communication systems, so in terms of both the network communication of the signalling system back to the control centre, but also onboard systems for the passengers, the third party communication systems to allow you to access entertainment. Line side mechanical and electrical, so effectively the plug sockets along the railway to power our line side equipment, so things like condition monitoring, the jet fans, all things that require power on the side of the railway need a power supply, an LV power supply. And then the track systems itself, which I'm responsible for. So we have obviously switches and crossings. Phase 1 in particular is a mandated slab track system, the same as phase 2A, and we have obviously the rail to consider. So one of our key interfaces is with the command, control and signalling contractors and the team that looks after that. And I'll come on to discuss that system in a bit more detail later. That of course feeds into the control center where the management team will look after the railway and control the train service, and also the depots that look after both the rolling stock, but also the plant and equipment that we will use to maintain the railway itself. And in terms of the detailed scope of all of these systems, there's a publicly available document, the link is included there, that actually sets out the detail of what each contract is set to deliver for those people that might be looking to see how they may fit into the scope of work that HS2 is delivering. So although rolling stock isn't a railway system, I thought there might be some interested in the rolling stock itself. So we're currently in the final stages of the procurement process for this. There's some legal issues that are being resolved at the moment, but the rolling stock itself is going to be a very advanced set of equipment. You can see the value of the contract in the top right there. It's a really significant investment by the UK. I've mentioned the pushing of the toilet technology on board, but in terms of passenger comfort, there'll be no first or economy class separation on the train. The layout of the train will be able to flex to suit different time periods. So in the morning peak, there'd be no premium class option, but through the day, certain carriages can be flexed to offer a more premium and comfortable setting for the passenger. And all our trains will be automatic, so they'll be ATO functional, and basically they have algorithms that will adjust their speed to suit the current requirement of the timetable. So whether that's catching up to regain time, or if the timetable is running perfectly, obviously to then optimize energy usage and not run at 360 kilometers an hour where it's not necessary. So tunnel systems and M&E. So I mentioned the need for ventilation. Obviously, we need to consider emergency scenarios where we may have train fires or within the tunnel, or other needs for evacuating a train within the tunnel. So we have ventilation systems to facilitate that. We also have cross passages in terms of during that process, allowing evacuated passengers to traverse from one tunnel into the adjacent tunnel into a position of safety. And again, in the top right there's just an indicative value of the two sets of contracts there. So we have a separate supply contract for cross passage doors to ensure consistency through the route across the different civils areas I mentioned earlier. And part of this contract also includes that line side LV power supply along the route that I mentioned that the other rail systems will call upon to power their equipment. So I've termed this power systems, but this is two systems combined really in the HV power supply, which takes that national grid and distributes it along the line of route. That then feeds into the OCS system, the overhead contact line, and that in turn powers the train. So the awarded contract for the supply of the OCS system is SNCF. They're providing an adaptation of their standard overhead line system to us, and it's been retermed V360, and that will become a standard route-wide design for the overhead line equipment along the route. And then the contract which is out for the supply chain is more focused around the installation of that system. The design is a standard client-owned design. So the CCS system, it will be an ETCS level 2 signaling system. There's some certain aspects of the functionality are very challenging, particularly when it comes to the level of automation, but the high density of traffic flow. So particularly around the Delta Junction, as the network feeds off to tie into Birmingham Curzon Street, and we have all the services that will be flowing from northern section of the route into Birmingham Curzon Street. We've got very tight technical headways between the trains down as low as 120 seconds. So that creates some real challenges with also trying to achieve the automated train operation functionality. Obviously, with that system, we need long-term kind of legacy support. So there's a significant portion of that contract assigned to a long-term technical support option running into the future. So telecommunications, we will have a fixed network, and that's primarily for security purposes of how the CCS talks to the control center, how lots of safety critical equipment along the route, such as air quality sensors within the tunnels or in the stations, feeds back to the control center, and that is by a closed data transmission network. We also have radio systems or 3G, 4G kind of equivalents for the more third-party comms, so where passengers on the trains are using their equipment, or for operational staff on the ground that don't need a secure connection back in to receive data when they're looking at asset information on the ground. So one of the big pieces of infrastructure, as you would expect, is the depots themselves. So for phase 1 and phase 2A, we have 3 depot locations, one at Washwood Heath, just outside Birmingham's city centre. We have one at Calvert, which is approximately midway between London and Birmingham, and one at Stone, which is just south of Crewe on phase 2A. And the purpose of Washwood Heath is primarily as the rolling stock depot, so where the fleet of trains will live and be serviced and be put back into service once they've gone through their maintenance cycle. Calvert, the fundamental function of Calvert is for the main infrastructure maintenance base for the phase 1 route. So most of the kind of core equipment like the grinding train, any inspection equipment will be stabled there, but we have, in addition to that, strategic sidings and loops along the route to enable that equipment to be best placed for making use of the engineering hours overnight. And then Stone Maintenance Depot is more focused around just having strategic access to the phase 2A and phase 2B western route once that connection comes in. So in terms of high-speed track system design, I wanted to start off by very early this year we awarded the contract for the design and supply of the high-speed sections of the route. That was won by POR JV with their colleagues Vienna Consulting Engineers. So we're just in the initial phases of this contract, and we've completed activity 1 on the screen, which is to provide information into what will ultimately be the track build contracts, which I'll explain in a bit more context in a moment. But the remainder of the contract is around detailed system design, the production of operation and maintenance manuals and construction support into the track system contractors who will build the system itself. And this contract's split into 2 stages. So we're in stage 1 at the moment, which is activities 1 to 4 on the left side of that screen there, where the POR and VCE are working directly with HS2 as the purchaser, as the client, but then we transfer that contract over to the design and build contractors, who become the purchaser and the manager of the contract itself in the delivery phase. So where does that particular contract sit in the wider strategy? So I alluded to it there, but we've got 4 geographical design and build contracts on the route. So between London and Birmingham, there's 3 sections which are split into urban, central and north. But the nuance here is that the urban contract is also responsible for a portion of the leg from the Delta Junction into Birmingham. So they build and construct this section out of London through all the tunnels out of London, and also from Delta Junction through Bromford Tunnel into Curzon Street Station. And then the other 2 sections on phase 1 are just the remaining portion of the route in the north and in the centre. And then separately to that, to align to the contract boundaries of the civils with phase 2A, we have a separate design and build contract for phase 2A itself. So I've mentioned the precast slab track supply. We have 2 other material supply contracts. Switches and crossings and rail expansion devices will be a similar arrangement, where for the first stage of the work we agree a common design as the client directly, that we then make that design and that contract available to the geographical design and build contractors to install that system. And then rail is quite simply a material supply. So in order to prevent kind of supply conflicts and to get value for money in terms of the material supply, HS2 is taking ownership of the rail material supply, which will then be issued out to the design and build contractors to install. So an overview here of the quantities for the supply contracts themselves. So the left-hand 3 columns align to the precast slab track systems design and supply. So we have quite a significant amount of route in tunnels, but the priority of the design to date has been around over earthworks. We also have a significant amount of bridges and viaducts. And again, I'll come on to discuss the integration with structures later on. The S&C and RED supply contract have got significant volumes, and in particular the S&C quantities here are exclusive of what's needed in the depots. but the contractors responsible for building the depots will be free to call upon this supply contract if they want to. And with the exception of Calvert Depot, which is aligned to the design and build contractor for the central part of the HS2 route, so the track contractor is also responsible for building Calvert Depot. So the POR system itself is a precast system. The dimensions and some photos are shown here. The reason we went for precast in particular was in terms of looking at the detailed programming of installing the track between London and Birmingham, when compared to a ballasted approach, which would have had to work out of a railhead and you effectively build the track in front of the section of track you've just built. We recognise there's a really significant program benefit in doing this, and that was around 15 months for the phase 1 route alone. So that was a significant opportunity, and alongside other kind of key benefits for the build stage around quality control and more longer term in the operation, having that ability to replace track systems as they become life expired, or if we have issues that require replacement of that slab itself. The decision itself was a £100 million plus capital investment decision. It went all the way up to Department for Transport and took over 2 years to go through the assurance processes and the governance to sign off that decision. So there might be a perception that, you know, we're, as a client, we're always pushing to effectively do things as cheaply as possible, but the value for money argument is really important. So if you saw the figure on the previous slide, that the whole track package is around £1.9 billion worth of investment, which makes around 3 or 4% of the phase 1 expenditure. But in operation, we can, if we kept the traditional approach around ballasted track systems, we might expect 30 to 40% of our operational expenditure on maintenance and keeping the railway running to be expended on the track system itself. So this was a long-term whole life cost decision that led to us going down this approach. And then further to that, the precast system in particular had strategic advantages for construction and then operation and maintenance. In the bottom left there, you can just see a brief schematic about the different layers to the system. So the precast element itself sits on top of a bearing layer, a concrete bound layer, as it's labelled there. So that bearing layer is cast in situ using a paving machine, and then the precast system is installed on top. The precast system itself will be made in a bespoke manufacturing facility, which is undergoing planning at the moment. It's been strategically sited close to the quarry source so that we're reducing handling of materials prior to actually casting the slab itself. Again, it's strategically placed with the opportunity for a rail link. So we're looking at opportunities to increase the proportion of deliveries of those precast elements via rail rather than road, and obviously the stakeholder benefits that yields. And as we look to develop the phase 2B route and the track system, particularly on the western leg, looking at having slab track on the western leg and increasing those quantities that we can deliver by rail is only a good thing. And obviously it's being set up initially to produce the precast track system for HS2, but strategically for the UK industry, having this new facility close to a quarry source with the expertise around precasting has benefits for the wider construction industry. So it's not just about HS2 in terms of making the investment. Department for Transport recognises that there's wider strategic benefits in us doing this. So I mentioned the construction method, but some images here, and I'll just explain it. So in the top left there, you can see that the first layer of the system that's cast in situ with the paving machines already in place. And then the precast panels arrive and are either lifted by simple plant and equipment or gantry systems. So the actual requirements of plant and equipment for installing are far less onerous than for large-scale ballasted track installation. we have relatively few operatives on site, and we can we also want to use the advantages of that to increase the number of work fronts where we can work at a single time, and that's where the program benefit comes for the wider route, because you're able to work in multiple places at the same time without the need for lots of complicated plant and equipment. So as the precast slab is placed in situ, it's obviously aligned and leveled. There's then a grouting layer that's placed in between the voids and the slab there, which flows in and around the slab and has adhesive properties to tie it into the bearing layer that's already been placed. The particular method we're using on HS2 is that this will be done without the final rail in situ, which has particular challenges around the survey accuracy and how we control that, which we'll come on to. But it's, as I said, we're very, very keen to realise the benefits that this precasting technology gives us for construction in particular. Here's a photo of an example of the completed system itself. It's interesting here to note as well, just to point out that it's showing a transition onto a longer viaduct. The noise barriers, which are common to HS2 as well, we have particular challenges around achieving noise and vibration requirements. So we have the same design integration issues around space with noise barriers and cable containment and OCS equipment. So I'll go on to talk about some hot topics. So starting with track alignment and track quality. There's a few aspects that we're considering in relation to achieving a very high track quality after installation. Obviously, that's important to us because it has particular implications around noise and vibration in particular. For certain wavelengths, we want to ensure that we're achieving a very tight installation tolerance. In doing so, one of the things we've developed is what we've referred to as the virtual test track in collaboration with the University of Huddersfield. So obviously a key contributing source to noise, the noise at source, is the rolling stock. So we established a virtual test track, which was taking the alignment design of HS2 and then superimposing on that track irregularities, which we sourced from both Germany and Spain as examples for slab track systems. So we can do some early modelling and basically optimise designs for both the noise barriers, but also how we're approaching specifying the track system itself in terms of noise and vibration. We have very tight tolerances around achieving the track alignment. Sorry, Paul, something just flagged up for me there. Was that a question?
Sorry, Matt. Yes, yeah, just a couple of questions that probably worth you having a look at this time. You mentioned this, a question from Phil Holborn. Where is the manufacturing facility for the precast slabs to be located, and why isn't the inclusion of the rail link a simple essential from day one, rather than being an opportunity that may be optioneered out?
So it's sited in Somerset. We didn't make it a mandatory requirement for the rail link because that might have overly constrained where the potential contractor could site their facility. But clearly, we, as part of the engagement with them, we asked them to consider this, and it's an opportunity that's been presented to us, which we will absolutely try and realise. But it was felt at the time that it would overly constrain the requirements of the contract if we were to mandate that. But yeah, it's definitely an opportunity that can be realised, and we're keen to do so.
Sure. So knowing that part of the area, I think there's quite a lot of rail-linked quarries in the area. I think that could be quite significant challenges in pathing trains from Somerset to the work sites.
Yeah, absolutely. Yeah.
Okay. Another question was from me. the previous slide that you showed, the completed system appears to show an asphalt base. Is this the case? And what approaches do you see? What advantages do you see in this approach?
So the asphalt that's shown there, if I go back to the image and I'll explain it. The asphalt here is actually, the asphalt shown here is actually it's a capping layer, so it's not the base on which the track system is founded. So it effectively serves as the drainage or the capping layer to the track system once it's installed. So it acts as drainage. The layers below are that concrete bearing layer I mentioned before, which sits on top of a granular layer of engineered fill, which is the top part of the earthworks system, or referred to as the protection layer. So the asphalt here isn't actually the bearing layer for the track system. It's placed after the track system is installed.
Okay, cool. Thanks for that. Sorry to disturb you there, Matt.
No, it's all good. Yep, thank you. So yes, we've got aspirations to achieve very high requirements around the track geometry. Clearly, a key aspect of that is how we achieve it in the field. It's all well and good designing it on a system, but in terms of survey control and delivery on site, we know that's a big challenge. We don't want accumulated errors along the site, and one of the things that has been established for HS2 and is common on other long linear projects like the West Coast Main Line, for example, is to establish a bespoke survey grid for the project. So this accounts for the distortion you would get if you didn't account for how the profile of the earth changes as you run along very long lengths. So the Ordnance Survey network is really good for kind of isolated coordinates for and small work sites, but when we're trying to build a long railway, we need to account for the distortion of extrapolating that. So it basically allows us to design in the coordinated space in our modelling system, and how we then achieve that on site. It leads to particular requirements around the survey grid as well, and we've got particular requirements for the track design and build contractors to set up a very tight survey control network. But that's absolutely necessary, particularly as I mentioned before, we're going for a method where we install the rail after the core track system itself has been installed. So earthworks interactions are a really key topic we've put a lot of focus into over previous years, and one of the key things I wanted to bring up was the requirements around shear wave velocity. So obviously, if we take an embankment as an example, or the new materials to the embankment, we can specify and achieve a very high level of specification, and deeper materials in the existing ground have consolidated and achieved a state of high stiffness just inherently. Where we have concerns is the top 2 to 3 meters of existing ground, and achieving particular dynamic requirements of that material, because the effects of shear wave velocity where trains are running at particularly high speed, effectively pushing that bow wave in front of it and creating high displacements can have effects up to 10 meters or more. So even on relatively high embankments, we need to be considering the particular requirements of the top layers of that existing ground level. How we do that is we've established in collaboration with ARP a design model which takes into account the particular soil parameters we're specifying, but also then backfits it in terms of assessing the relationship between static displacement and the dynamic displacement of running the train at our design speed. And we often look at the ratio between those to see what's acceptable in terms of requirements of the track system. So a further topic around earthworks is the long-term settlement and heave issue around building relatively large earthworks in a very constrained construction program for the mainwork civils means that we really need to understand how those assets are behaving longer term. And how we're going to manage that is we've established a kind of risk-based management tool based on a process they apply in Germany to take on-site monitoring data and effectively risk grade the route to understand where we can proceed with track installation. And it will one of the advantages of the precast track system design is that should we have isolated sections of route where we can't install due to compliance issues, and the same potentially applies for bridges and viaducts or tunnels which may have program challenges, that we can work around those sections of the route that are unavailable and continue with the track system installation itself. So it's not all about managing the risk and responding to the risk of potentially delaying track installation. There's also significant opportunity here that clearly we're a majority of the time trying to be on the conservative side of earthworks design, and the time it takes for the earthworks to settle, we would hope in a majority of cases will be way inside what the design assessment tells us. So we want a process which gives us that evidence to then realise the opportunity of being able to install the track rather than waiting longer term for what the design told us, the timing, the design of the earthworks told us to wait for. So sound, noise and vibration is a really key topic that we monitor closely. In the top right there, in terms of ground-borne noise, the traditional approach is to specify the track system in terms of insertion gains. So doing a relative assessment of the track system you're proposing to a known reference system, and how effectively how much that system damps the potential for vibration from the wheel rail interface through the tunnel invert and out, and the transmission through the surrounding ground to potential receptors nearby. So we've done advanced work to specify those levels, and we've got two performance requirements as it stands for the route. So predominantly the urban contractor needs to meet a high level of performance for the track system, so that we're meeting our commitments around that ground-borne noise and vibration requirements. In terms of open route and airborne noise, I've mentioned the barriers in the photo that was brought up before, but it's also quite important in the open route to consider what we refer to as the acoustic frequencies of the fastening system. So our precast track system design contract will also be nominating a fastening supplier. So we need to be sure that the performance of that system within these particular frequencies is adequate, because perhaps people on the call are familiar with kind of static or even dynamic stiffness properties of rail base pads, but when it comes to acoustics, we're interested in much higher frequencies, and that has particular challenges of how you accurately measure that in the lab or undertake testing to actually demonstrate. That's quite difficult, as you can imagine, with the frequencies. So that's a topic we've looked into in terms of how we've specified the track system itself. So integration with structures, particularly bridges, there's been a big challenge here around obviously the ambition was to have the precast track system designer on board circa 18 months ago for this very topic. That was the kind of the really key stages of the structure designs, particularly for long viaducts, where we were looking to integrate the track system design with the designs of long viaducts. So what we did was we commissioned various reports and worked ourselves into the parameters that actually informed the bridge designers. So typically the administration would tell them on the continent, the parameters they need to design for. So we engaged with ADIF, with Deutsche Bahn, with SNCF to look at what requirements were appropriate for designing bridges for slab track. And some of the key learnings we took away from that is being quite explicit on setting requirements around vertical and lateral displacement and discontinuities in particular, so abutments, and realizing the opportunity of using low tow load fastenings in combination with a higher rail stress limit, which is feasible for slab track, can have efficiencies in the structural design itself. And then separate to that, one of the key learnings we took around tunnel design was the need to avoid debonding, where issues have been seen with slab track systems and before have been attributed to debonding of the layers of the track system. So anything we can do to try and counteract that and to manage the water ingress in particular with pressure relief drainage in tunnels, for example, is only a good thing in terms of the track system design. So in terms of bringing all of that together, we've established a systems integration team at HS2. So again, to repeat the various different areas of engineering we have in the business, we have a systems integration team which sits above all of us, and their kind of remit is to effectively ensure the end state operation of HS2 is not compromised by any individual areas engineering decision making. And how we control that is to focus on what we call capability and functionality. So capability is of quite a definitive requirement of what we need to achieve. So that might be a specific journey time, it might be a particular noise emission level. A functionality will be around what we want to do in terms of how we apply speed restrictions, how we release a train from the station. And by focusing on those two elements, we're kind of removing the system influence of that, and the system leads and discipline engineers are all engaged to achieve either a capability or a function, and not just an individual requirement of their particular system. And that's how the contracts have mostly been specified. So out of that work, we are then able to specify system-specific requirements by linking them back up to the capability and function we need for the railway itself. So how do we translate that into longer term? Clearly, it's all fine designing the railway for day one, but our operational maintenance team have put a lot of effort into defining the strategy around how we monitor the network, either with line side equipment, but in particular for HS2, we're putting a lot of focus on the onboard monitoring systems. So out of the 54 trains we're ordering, 6 or 7 will have an enhanced onboard monitoring system for infrastructure monitoring purposes. So multiple times a day we'll be producing data that allows us to assess the condition, effectively the live condition on a day-to-day basis of the assets of the HS2 railway. And by having enough period to set up the learning of what that data tells us, we can then implement a preventive and predictive approach to our maintenance, rather than reacting to what that data is telling us. So part of the whole system integration strategy is learning from what other infrastructure programs in the UK have had to contend with. And indeed, the whole reason behind setting up the system integration function within HS2 above all the engineering functions is to achieve that culture of integration. So focusing on the functions and capabilities of the railway should help us do that. Focusing on the end state, as I said, that not losing sight of how individual decisions for contract areas, whether that be mainwork civils or stations or the track contract in isolation, we don't have impacts on the end state operation of the railway through decisions we take in isolation. some factors were alluded to on the CCS slide in particular, but technology development risk as well. So ensuring that enough time is accounted for in the program for integration, particularly of software. So for track engineers, it's quite easy for us to focus in on physical integration of steel, concrete, ballast, but where we've seen issues, particularly across rail, is through that integration of software and how systems talk to each other, the communication lines, not necessarily the physical integration of the works on the ground. So I just also wanted to finish here on stressing the importance of the strategic goals of HS2. So we've mentioned the capacity argument of the railway achieving 18 trains per hour and providing a high capacity to move trains from the existing network to release capacity there. Focusing on value for money. If we'd only focused on capital costs for the track system, we would have gone down the traditional approach of ballasted track installation and then realised the disbenefits of that in operation and high expenditure on maintenance. Focus on reliability. The customer wants a reliable service. They want to know that when they turn up to the platform, they can get on the train. That's time after time you'll see in passenger surveys, the biggest gripe is around reliability and knowing when the train will depart and knowing they will get a seat. And just to finish, I wanted to say as well, I think the biggest challenge we've seen is around skills and employment in HS2, getting enough people into the company, into the supply chain with the skill set to deliver has been an immense challenge, and I think everyone you talk to will talk to associated with the project would say the same thing. So there's various schemes to try and address that longer term, but we can't shy away from the fact that as of today, there's quite a significant problem around having enough capable people involved with the project. But longer term, things around the work experience program, apprentices involved with the project, we're looking to address that skills gap, but it's going to take effort from all of us to do that, I think. So that just leaves me to say, yeah, thank you for listening. And I think Paul will move on to questions now.
Excellent. Thank you very much indeed, Matt. That's very interesting. And just before we go on to the vote of thanks, there's a couple of questions in the chat for you. I wasn't going to disturb you in mid-flow. So first was from Rufus Ajeti. What is the minimum stiffness of the subgrade or formation layer?
So the top layer that interfaces with the track system, we set what we refer to as a dynamic stiffness requirement. So it's specifically EV2, if you're familiar with that testing method, but it's 120 megapascals using the EV2 means of measuring that. So it's effectively a plate test with a second cycle of loading, which imitates dynamic loading. So it's not a static stiffness, it's around a dynamic requirement for that interface with the track system.
Great stuff. Next question was from Dermot. What consideration have you given to weather resilience and climate change issues? E.g., how do you predict and cater for the unknown?
Yeah, really good question. This is quite a hot topic, and we have a whole team dedicated to climate change at HS2, but I think one of the biggest challenges I've seen in track system design is the interfacing with track drainage. So we're setting very onerous requirements around achieving drainage capacity along the route. But unfortunately, sometimes that can be interpreted in certain ways, which lead to designs of really quite obscenely sized drainage systems, even to the point where they're undermining the tracking places. So we need to be very careful, and we've kind of learned that lesson that we need to be integrating closely with the supply chain when they try to meet the requirements we set around climate change. Otherwise, it's open to misinterpretation or potentially over designing as well. So in terms of the track system itself, I think we recognise that in almost every case we've assessed, we consider slab track to be more resilient to the type of extreme weather issues we will see in the future than ballasted track. Yeah, I think one of the key areas we want to look into, and I know it's a topic that RSSB have raised, is around stress-free temperatures of rails long term. How do we assess and perhaps look at references in the continent, because we really wouldn't want to go towards seasonal stressing campaigns like some locations across the world. So it's all these topics are very much on the agenda, but not straightforward answers, I'd say. So yeah, it was a good question.
Yeah, absolutely. Last one so far in the chat from Alexander Baldwin. It was interesting to note the need for a rough tunnel surface. Have HS2 considered the health and safety risks associated with large areas of scrabbling, or have alternatives been identified that minimise HAVS issues?
Yeah, absolutely. So that interface in tunnels, that layer of the tunnel is actually a cast in situ layer. So what we've done is worked with the civil contractors who are responsible for tunnels, that as they're placing that in situ layer, they have a raking attachment onto the equipment that's installing the concrete in situ. So we're achieving the roughness as part of the concrete installation. We're not relying on a kind of post concrete install method, whether that's there are chemical treatments that achieve the same thing as well, but because we're installing the concrete, we're taking the opportunity of applying the roughness at the point of installation, not afterwards.
Great stuff. Thanks, Matt. Right. What I will do before I do the vote of thanks, I'll open the forum up for just the last chance to ask questions for about 15-20 seconds. And what I will do then, after that period, I will stop recording and we will go to the last part of the meeting. Okay, thank you very much all. I'll stop recording now.